All right. So this is just a 20 slide explanation of our proposal to DARPA's Luna 10 solicitation. Um, Specifically, we adapted our work on lunar comms that we for Moondao and got together with some other folks that were working on similar concepts and framed it as PNT, positioning, navigation, and timing infrastructure for Cislunar ecosystems using a few public domain technologies, so research and open source technologies that exist today. And to be cheeky, of course, we have to have a backronym, the Cislunar Open Clock Synchronization System, or CLOCKS.
Hmm.
Um, so from Moondao, it was me, Pablo, Greg. We had Jacob and Rachel from Open Lunar Foundation, Ramon and Felipe from Added Value Systems, or AVS, um, Ahmad Bayagawi from the Time Card, which is a part of the Open Compute project, and lots of contributions and help from uh, Nobu Shiga, who is the primary author on all these wireless two-way interferometry things. So just want to give a shout out to everybody else there. I think I forgot some people, but yeah. So just to set the stage for what we're looking at solving, um, positioning, navigation, and timing uh, is critical for mission operations at the moon. So specifically, we're looking at timing as this piece of it. It's involved in navigation, orbit determination and ephemeris, communications, um, and interacting with other missions, as well as just getting commands and collecting data from the moon. Two interoperability standards, LunarNet from NASA and Moonlight from ESA, um, are published and generally accepted by a lot of missions looking to go to the moon. Both have a stipulation in there that a precision timing signal will be available. And once you have it, here's what to do. But neither of them define the source of that timing signal. So, in order to have a scalable and accessible timing framework, we're going to use today's technology to get there. Um, the main focus of our proposal, or I guess a cornerstone of it, and all the organizations involved in writing this paper, is democratization of services. And not only does that improve access, but it also catalyzes coverage, distributes the capital investments across the population of missions that are going to the moon, um, basically as they go. So just some fundamentals here. Wireless communications are how spacecraft communicate with each other and with Earth. So it's a given that every thing that goes to the moon is going to have wireless comms. Um, we're going to present a method of precision timekeeping using those comm signals to achieve sub-nanosecond timing synchronization and sub-millimeter ranging between the two nodes, um, as a way to maximize coverage and resilience of such a PNT service. And we're not pitching a competition here with lunar global navigation systems like GPS, but for the moon. That's been the kind of de facto standard of what everyone assumes that will eventually be at the moon, is that sort of GPS-like um, constellation of satellites that you just need to get an antenna and you get your timing and ranging. Um, what we're proposing is distinct, but not, uh, it doesn't replace that kind of service. In fact, it complements it, fills in the gaps, and also does so as a bottom-up approach that grows with the population. So the first person that's there doesn't have anyone to really talk to. right? But as more people go and more people go and like land on the moon, go to orbit around the moon, the service grows organically, and we don't have to do this thing where we're operating without anything until finally the last piece of the GNSS constellation is there, and then all of a sudden you have all the coverage, right? There's no the current paradigm is really binary in that sense, and here we're presenting something that grows gradually. And lastly, democratized capability makes decentralized service models viable and incentivizes that interoperability that LunarNet and Moonlight um, are promoting. So the basis for wireless two-way interferometry, or YY, is that it uses the phase of the carrier frequency for a communication signal to it compares the I should just read what's on the slides here. Um, assuming two nodes, like a satellite and a ground station, or two satellites or whatever, have precision clocks and their wavelength is stable, their frequency is stable and not drifting over time. When those two nodes talk to each other, they can compare the phase of the waves, basically like the distance from peak to peak in their signals. And if we have the precision to measure that delta t to the nanosecond level, then from velocity is or position is velocity times time. The velocity of light is a constant. We measure the delta t, so we can just by measuring that delta t get the distance between them to 3 millimeter precision or better. So the reason why you would compare those two that phase to get the delta t is because you want to sync them. When you sync a clock, you want to just remove the delta t, and then both of those clocks are in phase. The clocks are synchronized, and since you compared and got the delta t because you wanted to remove it for your timing signal, you got the positioning, the ranging for free. That's the simplest way to put YY. It's been demonstrated on the ground, demonstrated uh, in mesh networks and between buildings on Earth to measure with this level of precision. It's been great. But it's not just a cool technology. It's the fact that all of these missions have comms, wireless comms, all of them. And so if we can measure the distance between them and also synchronize their clocks together with the existing equipment, basically all you need to add is this capability of timing, like having a precision clock, and then you can get all of this instead of having a fancy receiver or a whole separate signal path to do things. And so it's not like it's nobody's doing it, but that doesn't mean that it's novel technology. In 2019, YY was demonstrated with commercial off-the-shelf components on a Wi-Fi network. Time card, which is currently under review as an IEEE standard, is a PCI Express card that can plug into your desktop computer and do sub-nanosecond timekeeping. The hardware and software for that is both completely open source. Clocks, like actual oscillators that can keep precision time for the level that we're assuming it would need, those exist. You can buy them just on the internet. And as far as ConOps, like concept of operations here, two-way time and frequency transfer which is kind of the foundation of YY, was demonstrated with spacecraft between two clocks across the Earth in 1991. And as far as decentralized networking goes and decentralized framework to exchange services for networking between peers, in 2021, Helium launched and successfully commercialized a decentralized machine network for internet connectivity on Earth. So let's take it to the moon. This is just a slide to say what I just said because we didn't get to present this. We just had to send it. I'm going to kind of gloss over these. These are some technical details about the time card. Um, the time card itself is this. There's this CSAC module, this big shiny box on the card. That's the clock itself. The rest of the card is there to um, support that clock and also um, enable that 10 megahertz signal and the pulse per second signal out to other things. So it lets other things talk to the clock and synchronize with it. And it also has radios to be disciplined by GPS when we're on the ground. So it's already set up to do all the things that we're looking to do. And it was actually used as a core piece of the YY things. They actually work together with the time card folks. Um, so yeah, YY is a thing. It's being commercialized in Japan. It's cheap, it's so far it's been performant. The only thing is we haven't uh, done it with things on orbit. And when you're getting to orbital speeds, it's orders of magnitude different than driving a car down a highway, right? Which is basically the level that we've seen here in these experiments. That said, in the parking lot, YY experimentally demonstrated comparing two clocks with a precision of 2.2 picoseconds and measured the distance between them to better than 1 millimeter, which is insane. And lastly, Felipe from AVS basically did his PhD in lunar GNSS. So he derived like how much it would cost to put together a lunar GNSS system as our baseline, right? So there's DSN, Deep Space Network, which is how we currently communicate with lunar missions. Making some of these assumptions, the operating cost is $3 million for fiscal year 2022. Whereas if we had an 8-satellite lunar GNSS constellation at the moon, it would cost instead on the order of $350 million. What we're proposing is to take that one step further, and instead of waiting for that 8-satellite lunar GNSS and having one operator have all these costs, each little mission would contribute a little bit and incur about $5,000 of cost to implement the clock. And so as far as like making this a commercialized service, Helium is really our case study. So here, this is just a slide showing that like YY needs precision in the nanosecond, picosecond range. Time card PNT, in order to be used at a mission on the moon, needs about that precision, and time card provides that precision. So we're good, right? But we want to this proposal, the actual work, was to prove it. And we would do that using an agent-based model where each little dot has its own clock, has its own trajectory, and has its own communications frequencies and communications range. And so you put a couple of those around the moon and see how things go. You put tens, hundreds, thousands, tens of thousands in all these different orbits. And since we would control the simulation space and we would have visibility into each of the agents, at the end of it, we can do statistically significant analysis to see, okay, in general, how synchronized were these agents to each other, to the real like universe time? How much bandwidth did they have exchanged? Um, and things like that. And since it's just like a framework, and we would set up these agents and set up these instrumentation points in the simulation, we can do this decentralized YY thing where everyone's talking to everyone else and they don't really have a lot of range, but you know, do they have this level of precision? Or we could do the GNSS thing where there's a few um, transmitters and then everyone else is a receiver. Or we could see how things go across the population with both of those concurrently. Um, so we put together some metrics here that we would actually use, like quantitative metrics that we would use to assess the performance of Lunar GNSS versus um, decentralized versus a mix of both happening at once. And we could see how that would scale with the number of users. And this is what I just said. So where we would take that insight is to basically make it a baseline mission profile for our own little constellation to seed this service. And then also the hope would be that this would lead to an open source design for a time card that's built from COTS components under $5,000, and any mission could easily incorporate it into their mission. Um, Market analysis, there's lots of money to be made here if that's what you're into, um, which is what DARPA was into. But also, like this, even being open and public and open source and decentralized, there's still a lot of opportunity um, for individual actors to set up their own infrastructures. Maybe somebody has like a tiered network where you can get their baseline crappy but free service, and then if you pay, you can get millimeter level precision or better. Um, for the premium users, that's totally possible and enabled by this kind of framework with the same satellites and not having to send different hardware and not having to send a different protocol. Um, and similarly, this kind of solves the scaling problem where you don't have to worry about, as the population grows, naturally it supports itself better. Um, there's more routes for messages to take. There's more access to someone providing the time for you. Um, and, the networks would kind of self-organize and make a get basically benefits from this kind of scale instead of just suffering congestion. I firmly believe that we can demonstrate that this works, and uh, like in Leo, in low Earth orbit, just two CubeSats talking to each other. Maybe they're in different orbits, like orbits that cross each other, so you can see if they can exchange timing and ranging and synchronize their clocks when they're far apart, and also when they're moving very fast relative to each other. Um, with the satellites in orbit, you could uh, see what the performance is like to synchronize to ground stations. Um, and with more than one CubeSat, not only do you get the satellite to satellite interactions, but you also have two opportunities to uh, see how the time card works in space. So obviously, scaling that up would be great, but with a minimum of two CubeSats, um, probably take like $3 million, a year and a half for a university to build it from COTS components. It could absolutely demonstrate all of the core technology that we're showing here, and then we would have already done the agent-based modeling to show that it would scale, and that's it. That's all. That's everything. So it kind of depends on participation, really, and population. um, and we haven't done it in space before, satellite to satellite. The core technology has, but not in this way. Um, and like we would be proposing a time card which would provide this capability. Obviously, anyone could remix it or make their own completely from scratch, and it would be totally compatible. Um, but in general, speaking from experience, it is uncommon for precision clocks to be flown in space. Like most satellites just have a GPS receiver, and then their own clock is like a 5-cent part. Even if they had a $20 part, it would it could be enough, honestly. Uh, you know, uh, at least to be a receiver instead of a provider or a peer. Um, and when missions cost millions of dollars, uh, an elaborate setup, or I guess a performant one, like what we're presenting or proposing, 5K compared to $3 million for the whole mission. It's a really easy win if it's just integrating this for free and then using the other equipment that you would already have anyway. So yeah, this scales. It complements Lunar GNSS. It doesn't compete. It democratizes the capabilities, incentivizes interoperability, and makes decentralized service models viable. We can do this with simulation to completely instrument and predict how things would work in a number of scenarios over time, in different potential scenarios where the lunar ecosystem grows. Um, we have core metrics, and it's not just performance, but it's also mission metrics, cost, timeline, tech development, everything. And this is totally doable. Like I am 100% convinced, and I'm really excited to keep working on this with Moondao. Um, and our other contributors are super excited for it too. So I'm really excited to see how this goes. I know that was long-winded. I didn't mean for it to get that wordy. But yeah, we had some limits here. A paper that was limited to 10 pages plus references and 20 slides on that. So read it at your own leisure. Happy to talk either in the Lunar Comms chat, space chat, whatever. Um, and I'll be putting this on the Obsidian.
That was awesome. Loved it. Great presentation. Um, so excited for this tech. I just think it's just so awesome how many people contributed to that too. Phil was like just orchestrated like a dream team of like amazing contributors.
Yeah,
So
we're still in touch. So we've talked about how the process of writing it went at length. So I don't want to spend too much time on it, but yeah, we're still in touch with all the contributors, and we're still like throwing around different proposals that we can apply to. So um so excited. I'm just like jumping out of my skin here.
we're decentralizing the moon. But actually though, I mean this is like a man. Like the more I hear about this, the more like we tinker on this idea. It's just um it's so perfect in so many different ways. Just feels so right to that this is like the work that we're doing at Moondao. So yeah, it's awesome.